Okay, so welcome back. Okay, so now what we're going to do is we're going to use the idea of Riemann sums, and we're going to find the area under the curve, because the next question is now that we've dealt with derivatives and we found the equation of a tangent line, we found second derivatives, so now the question is how do we find the area under the curve? For example, if I gave you something like this where I have a cycloid, right, and I want to find the area under the first revolution of the cycloid, so the first here, right? So I've given you this, let's say I've given you these parametric equations that represents the path of a cycloid, and I want to find the area of the curve from 0 to 2 pi, for example. How would I do that? Well, that's what we're going to discuss in this video. So, what I've done is I've taken an example of a curve, so I basically took part of this and stuck it down here, and so this is the general case. If I have a curve, how do I find the area under the curve? So we're going to use triangles to approximate this, right? So I've got all of these values, right? So I've got subdivided intervals, and I've got rectangles. So how do we get to here? Well, let's start with the general case. Let's say I have two parametric equations over the interval for t between the interval a to b, okay, the closed interval a to b, okay? And let's say x of t is differentiable, okay? So what we do is we start by subdividing the interval from a to b into equal subintervals. Okay, so just like we did before with x, but now we're dealing with parametric equations, so we're dealing with intervals of t. Okay, so we're going to subdivide this into equal pieces, equal intervals, equal subintervals of t, where t0 equals a, and then of course we have t1, t2, all the way to tn, which is equal to b. So we subdivide the interval a to b into subintervals, regular subintervals. Okay? Now, then what we're going to do is we're going to take a point on the interval in each subinterval. And we'll call this t bar sub I. Okay? Where we're just taking some t value in the ith subinterval. Okay? We'll call this t bar sub I, or t sub I bar. Nah, I like t bar sub I. Okay? So now how are we going to use the, so we're going to use the rectangles again to approximate the area under the curve. So how do we do this? Well, we got to find the area, which is base times height. Okay? Same thing we've done before. So what's the height of this thing? The height of this thing is determined by the parameter of y of t. Right? So, but we're going to use some value, right? So we're going to use some value on the ith interval. Okay? So we would use t bar sub I. Okay? Or in this case, since we're between 0 and 1, so this is x of t sub 0, right? So again, we're using our regular subintervals of t, right? But remember, every t value gives us a corresponding x and a corresponding y. So we're going to use t sub r. So we're going to use x of t bar sub I for each subinterval. So for this one, it would be t bar sub 1. And then, of course, this would be t bar sub 2 all the way to t bar sub n. Okay? So again, just to clarify, all I'm using is some t value within each subinterval. And I'm using that to get the height of my rectangle. Okay? So now the height of my rectangle is going to be what? Is going to be y of t bar sub I. That's going to be the height of my ith rectangle. Okay. Now the width is going to be what? It's going to be the difference between, right, the two endpoints of my ith subinterval. So that's going to be what? It's going to be x sub I minus x sub I minus 1. Okay, that's going to be the width. Now, if I put this together, right, so let's put this together. And so the area for my ith rectangle, call it a sub I, that's going to be equal to the product of these two. So that's going to be y of t bar sub 1 or t bar sub I times x sub I minus x sub I minus 1. Okay, so this here represents the area for one of the rectangles. Okay, but we're not done. So now what we're going to do is we're going to use a Riemann sum for the area. And so what would the Riemann sum look like? Well, I'm going to add up the same thing for each one of these rectangles. So I'm going to put this in a sum because we're going to sum this from I equals 1 to I equals, or excuse me, I equals 1 to I equals n. So now let's go back here. I'm going to erase some of this. Okay. Again, you should have this in your notes. So now what we're going to do is now we're going to take this result and create a Riemann sum. And we're going to add all the rectangles from A to B. Okay? So that means our Riemann sum, so the area is going to be approximated by the Riemann sum, which is the sum for I equals 1 to n of what? Of this. So it's going to be y of t bar sub I times x, oh, hold on. Sorry, I messed up here. This is not x sub I. I'm used to this. I got to put in terms of t. So let me change this a little bit. So this is x sub t sub I. That's what I wanted. X sub t sub I minus x sub t sub I minus 1. Remember, these are parametric equations. Okay, so again, it's I reverted back to x. Okay, so then our ith rectangle has an area of y of t bar sub I, and then the width is going to be x of t sub I minus x of t sub I minus 1. Okay, so that's the width of the rectangle. Okay, now, so now this is going to be this. There we go. Okay, so now taking one of the rectangles, right, base times height, and then I'm summing up all of the rectangles to get the approximate area under the curve. So this will give me the approximate area under the curve from A to B. T equals A to T equals B. Okay, so now that I've got that, let's kind of manipulate this because I need a delta T in here. And I don't have one. Okay, so what's delta T? Well, delta T right? Because these are parametric equations in terms of t, so I need to get a delta t in here. So what's delta t? Well, remember, delta t, because these are regular subintervals of t, is just going to be t sub I minus t sub I minus 1. So all I'm going to do is I'm going to multiply the top and the bottom by this. Okay? So what I'm going to do is I'm going to multiply the top and the bottom by that expression. So let me write this out first. So I'm going to multiply the top and bottom by t sub I minus t sub I minus 1 over t sub I minus t sub I minus 1. Okay, so that's all I did was multiply the top and the bottom by this, which is just delta x. Right? So this is delta, or not delta x, delta t, right? So that's delta t. And so why did I do this? Well, because I need a delta dt here, because when I go to take the limit of this thing as n goes to infinity, then what happens? This becomes dt, this becomes dt. I need the derivative out here. Well, what happens with this one? Well, this is going to correspond to this. This is going to match with this. So when I take the limit, this is going to become the derivative of x, because here's what's happening. As I take the limit of this thing, the difference, the distance between these two is getting smaller and smaller and smaller and smaller, right? And so this is getting smaller and smaller and smaller and smaller as well. So this is going to x of t sub I. Well, actually, it's going to x of t, and this is becoming dt. So this is going to be the derivative of x of t with respect to t. So I'm going to get x prime of t here. Okay, this is just going to be y of t. This is going to be the d of x dt, dx dt, and this is just going to become dt. Okay. So let's do that. So now now if I take the limit, a is going to equal the limit as n approaches infinity of the Riemann sum. As I goes from 1 to n of y of t bar sub I times x of t sub I minus x of t sub I minus 1 delta x, or excuse me, delta t, right, over delta t. And so now, just like what I said before, all I'm going to do is take the limit. So what happens? This becomes y of t, right? So the final thing, the summation becomes the integral. So this becomes the integral from a to b, right? This becomes y of t. This becomes what? This just becomes x prime of t. And this becomes dt. And we get the result. And that's how we find the area under a curve, under a parametric curve, And so in the next video, we're going to introduce the theorem. And then we'll do an example, probably this one. Have a great day.